Few more expressions. Let's talk about this expression, 1,000 to the log 3 power. Now, when I see this problem, I look at it and I think, wow, it would be nice if that 1,000 wasn't there. I would rather this look like the following, 10 to the log of triangle, because we learned that 10 to the log of triangle was just triangle. Okay, so the question is there a way we can take this expression that we have here and rewrite it, okay, so that we end up with something that's 10 to a power? That's it. So we can think of this as 10 to the third power to the log 3. Okay, that's great. And this looks a little bit more promising because now I have a base of 10, which is what I wanted. I didn't want this base of 1,000. Okay, so far so good. What do we do with exponents in a situation like this? That's the question you should ask yourself. Yep, and what we do is we get 10 to the 3 times log 3 because we can multiply exponents in that situation. Alrighty. Now, it almost matches up with my special rule I have here over on the side. The only problem is this rule does not have a coefficient in front of the log. The log triangle just has like a 1 in front of it, but this log 3 has a 3 in front of it, and I don't want that 3 there. So the question is, do we know any rules of logs that we can use to get that 3 away from the front of the log? So the answer is yes, we do know something. If we think of this rule, we learned the rule that if we have log of a to the c power, that's c times the log of a. What that's telling us is that if there's a coefficient on the log, it can come up as the exponent of the thing we're taking the log of. So we can rewrite this as 10 to the log of 3 cubed. Okay, and then basically I claim we're there. I mean, this is exactly of the form 10 to the log of triangle. The answer to this is just triangle, or in our case, 3 cubed, which is 27. So it's very handy to be able to rewrite your base some other way. So let's try a different one. What if you had the following: 1 over 100 to the log 7. Here's what we can do. We can take this 1 over 100, think of it as 1 over 10 squared. But that's still not quite 10 to a power, but that we can think of as 10 to the negative 2, and we go, we got it, right? So this becomes 10 to the negative 2 to the log 7. All right, great. Well, we know we multiply exponents in that situation, so it's 10 to the negative 2 log 7. And the only thing that's bothering us, or should be bothering us, is this negative 2 in front. We don't want that. So we'll make it the exponent because of the third rule of logs that we proved. 10 to the log of 7 to the negative 2 power. All right? That's really 10 to the log of 1 over 49. Because the negative 7 to the negative 2 power means 1 over 7 to the second power, right? Or to the 2 power. And then you have 1 over 7 squared, which is 1 over 49. And now when we're done, we have 1 over 49. Okay? All right. It's worth making a comment about that. Let's just go back to one part of this problem, right here. We have an option, actually. We could rewrite that as 10 to the log 7 to the negative 2. And we can do that because we know we're going to multiply these exponents here. And we know we can multiply in either order. So that means the log 7 could have been here and the log 2 could have been there. You still would have had the same product. Now the advantage is 10 to the log 7 looks exactly like our special rule. So this thing on the inside just equals 7 to the negative 2 power is 1 over 49. So you can kind of get to use that idea about 10 to the log triangle sooner if you just switch the order. All right, let's think about something that's kind of like this. Ready? What about this question? Log of 1,000 to the 2x. Okay, so I'd like to simplify this a little bit. It looks a little bit like this rule. the log of 10 to the triangle, which we know is triangle. The problem, of course, is that I don't have 10 to a power in our problem. So I'd like to rewrite it as 10 to a power. Do that. So let's rewrite this as the log of 10 to the third to the 2x. Okay, and 10 to the third is 1,000, so I didn't change the value of anything. That's okay. You should ask yourself the question, what do you do with exponents in the situation? You multiply them, right? It's actually sort of fun. There's two ways we could go with this. I'm going to stick with this method for now, and then we'll talk about what else you might have done. So you can think of this as log of 10 to the 3 times 2x is 6x. And then I get to use this rule that I love, this rule over here, and I get just an answer of 6x. Now, I'm thinking of the third rule of logs, right? The third rule of logs says if you have, again, log of a to the c power, it's c times the log of a. You can use this rule in either direction. In the previous problem, I think we went like this, but in this problem, we can go like this. Watch. What we can say is that 2x could come down in front, just the 2x part. You'd have 2x log of 10 to the third. But 10 to the third is just 3. So this becomes 2x times 3, which is 6x. You still get the same answer as you did before. All right? Just a slightly different way to proceed. Here's another one to try. Try this one. Log of 0.001 to the x. See if you can rewrite that. Ready? You could think of this as 1 over 1,000. And if you do that, then you know it's 1 over 10 cubed. And that's all it takes. That means we can think of this as the log of 10 to the negative 3 power to the x. But that's just the log of 10 to the negative 3x. And we know by our special rule that this is negative 3x. Just to remind you, this expression is asking you a silly question, right? It's saying, what power do you put on 10 to get 10 to the negative 3x? If you listen to that question, you know the answer. Okay? All right. So let's see what other kind of log problems we might encounter. Here's another one. So suppose I start with something like this. I tell you that x equals the log of a, and then y equals the log of b. Now I think it's worth doing this right away. You should know that you always have the option to write these in exponential form. So each one of these things has a corresponding exponential equation. So the thing to remind yourself first is don't forget this is really a little base 10 here. Here's a little base 10 here, even though we didn't write it. So this is telling me, if I look at the right side of this equation, this is saying, what power did I put on 10 to get a? And the answer I'm getting is x. So that must mean that 10 to the x is equal to a. All right? And then in the same spirit, it's the same question. It's saying, what power do we put on 10 to get b? And they're telling me the answer is y. That means that 10 to the y must equal b. So just keep that in mind as we proceed through some of these questions. So, can we write expressions for things like this? Express the following in terms of x and y. That's what we're asking to do. So suppose I had given you the log of a times b. Could we write that in terms of x and y? Let's try a few more while we're at it. Let's also try the log of a cubed times the square root of b. And then one more, just to get us going here. How about this? A times b. All right? Give those a shot. Pause for a minute. Take a look at these things. The first rule of log says that this is really the log of a plus the log of b. But that's just x plus y. So we achieved the answer to the first one. Now for the second one, you do a little bit of extra thinking. Okay? You have a product of two things. You can see you have a cubed times rad b. And we know from the first rule that that would be the log of a cubed plus the log of rad b. Okay. Well, I can't really just say x plus y because log of a cubed doesn't equal x and log of the square root of b doesn't equal y. But the third rule of log says that if I have an exponent, I can put it in front. So I can make this 3 log of a plus 1/2 log of b. So you just needed to remember that radical b, or square root of b, is really b to the 1/2 power. Well, now you're set. This merely means 3 times x plus 1/2 times y. So there we go. We've succeeded in writing this in terms of x and y. Okay, that last question is meant to... the goal was, keep the instructions in mind where I said write this in terms of x and y. Well, you can see how at the beginning of this, when we were mentioning that each of these log expressions has an exponential form it can go in, and here it is again, you can use the exponential forms to do a times b. A times b would be 10 to the x times 10 to the y. And that's okay, because that's in terms of x and y. Now, if you want to simplify it a little bit, you can. The bases are the same, so you could write 10 to the x plus y power, right? And you would be okay there. All right, let's look at a few others. Let's try this. Suppose you had this expression, the log of a minus b, versus, compared to this, the log of a divided by b, versus the log of a over the log of b. So try and rewrite those in terms of x and y. Okay, for the first one, it's tempting to think, oh, it's like Rule 2. But it's not. Rule 2 says that the log of a divided by b is the log of a minus the log of b. That's the second rule of logs, and it applies to this question. It does not apply to that question because we're not taking the log of a minus the log of b. So this is put here to trick you. What can you do? You can say, well, this is the log of 10 to the x minus 10 to the y. And that's the best you can do there. You can't distribute a log onto that. Logs do not, as functions, do not distribute across sums and differences. That's the best you can do there. Some people might be thinking, all right, well, how come we can't just put the log of 10x minus the log of 10 to the y and see what happens? Let's just go to a simple example for a moment. So suppose you had the log of 100 minus 10. Okay? So we know we can subtract 100 minus 10. So this is really the log of 90, which means what power do we put on 10 to get 90? Now, I'm not sure what that is. I know it's a little less than 2. Okay? If you thought that logs could be distributed, you'd be saying, hey, this equals the log of 100 minus the log of 10. Now, I can do both of those. The log of 100 is 2. The log of 10 is 1. 2 minus 1 is 1. Okay. So the question is, does 1 equal the log of 90? Are these two things the same? If they are, then maybe you can distribute logs. But clearly they're not, because the power you put on 10 to get 90 is not 1. So this means that distributing logs onto quantities does not work all the time. Okay, so let's go back to another problem we were looking at. Here it is. Somewhere I lost it. So here it is. All right, this is just x minus y, so that's done. And then for this last one, the log of a is x, and the log of b is y. So that's what you can do there.